Hey guys, in this video we're going to find volumes of revolution using the washer method. And so we're going to do a little bit of an exploration with what we know about two-dimensional shapes before we go any further. So this picture over on the right of your screen is a washer, right? A washer is a solid ring with an open circle in the middle. So we want to find the area of this washer. What we need to think about first is the fact that this is really a big outer circle with an inner circle subtracted out. So I would take this and I would say, okay, my outer radius here is 2.5 because my diameter is 5. My inner radius here is 2 because my diameter is 4. And so what I know is that that ring has a width of 0.5. And to calculate that area, I would do the outer area. So pi times 2.5 squared minus the inner area, which is pi times 2 squared. And again, the reason I'm doing that is because I'm doing the outer minus the inner. I'm taking the area of my whole circle, right? And then I'm subtracting out the area of my inner circle to just get that ring on the outside. So in general, what would my formula for this be? Well, if my outer radius is a capital R and my inner radius is a lowercase r, my formula for this would be pi r squared, capital, so that's my bigger ring, minus pi little r squared, right, which is my smaller radius. And I could factor out a pi there and think about this as pi times your outer radius squared minus your inner radius squared. Either of those would be totally equivalent formulas for area. So now let's consider this function. And we're going to revolve this just like we did with disks, but we're going to get a different looking solid here. So I'm going to revolve this area around the x-axis. So it's going to come down and around like this. And the outer part's going to be curved, almost like a bowl. And then the inner part's going to have that same kind of curve. And we're talking three-dimensionally now. So I always think about this almost like a cereal bowl that looks like it got inflated on the inside, right? And that's going to be what my solid looks like. So what would the cross section look like? Well, let's think about it. If we slice this down perpendicular to the x-axis, we'd be coming through like this, right? And I would have that outer radius, which would be this and this. And then I would have the inner radius, which would be what I'm highlighting, this and that. And so depending on where you were, that inner radius size would change. So it's going to look like this washer over here. And so what I want to do here is think about my outer radius, which would be from the center to that edge, and my inner radius, which would be from the center to that edge. And what would those be here? So thinking about this from the center here, which is the x-axis, to the outer edge, well, that's going up to my square root function. So my outer radius here would be from 0, which is my center line, to square root of x. So my outer radius on that would be the square root of x minus 0, or just square root of x. My inner radius would be doing the same thing except going from my x-axis, my center line, up to my inner function, which is x squared. So my inner radius here is x squared minus 0, right? Outer radius is square root x, inner radius is x squared. So what I wind up getting here, and again, I'll do it here in case we want to see it again, this would be your square root x. This would be your x squared. Those are your radii. So the integral to find the volume here, well, we know the integral is the accumulation of area, right? So the area there would be pi times your outer radius squared minus pi times your inner radius squared. That's the area of that disk. So it would be pi times the square root of x squared minus pi times x squared squared. So that's my area function. And now I'm going to integrate that with respect to x from 0 to 1, my x values. So a general equation for volume of a washer is exactly what we just talked about. Take your cross-sectional area, which is this, and integrate with respect to your variable over that interval. Same thing if we did it with respect to y equals -1, right? We take this region, we rotate that around, that's my inner radius, that around, that's my outer radius, and we wind up getting that type of shape where, again, we have an outer radius and an inner radius. We don't always have to revolve around an axis. That's okay. So this is our method for volumes of revolution. If the volume of a solid is retained by rotating around a region perpendicular to whatever axis, and the cross sections are washers or rings, we're going to do pi, we could factor that out to the front, the square root of your outer radius squared minus your inner radius squared, whether that's in terms of x or y. So let's look at this one. We've got the region bounded by y equals 5 and x squared plus 2 rotated around the x-axis. So I'm rotating around this as my center line. So what's going to happen here, I know that this is my two intersection points. So the region I'm talking about rotating here is this region in red. So rotating that around, my outer radius is going to come down like this. Right here it would come down like this. And notice that's almost going to look like a cylinder, right? Because this edge is flat, so that edge would be flat. And then the inner part, let me switch to orange, is going to rotate around like this. And so you're going to get this shape where it's like a cylinder with an hourglass cut out of it, right? And so that's what my solid looks like. When I slice it, I would get a ring, right? So let's think about this. I know that I'm going to do pi times the integral of my outer radius squared minus my inner radius squared with respect to x. So let's think about what those are. So pi is just going to be pi. Integral, and we'll talk about bounds in a second. My outer radius here, we're going from the center to the outer function, which in this case is y equals 5. So it would be 5 squared. Minus, now we're going to go from the center to my inner function, which is x squared plus 2 squared dx. And so that's my basic setup. Now what are my bounds? Well, let's look at that region. That region goes from right there to right there, and I want the x values. So what I'm going to do is I'm going to set these equal. X squared plus 2 equals 5. X squared equals 3. So x equals plus or minus radical 3. So this is going from negative radical 3 to positive radical 3. And then I could integrate that and I would get my volume. All right, let's look at the next one. We're going to rotate this one around the x-axis again. So we're going around this axis and I'm rotating this region. And so let's start by finding our intersections. We can guess where they are, but we can also confirm that. Let's set these equal to each other, right? And so I get x squared minus x minus 2 equals 0, which gives me x minus 2, x plus 1 equals 0. So x equals negative 1 and x equals 2, which seems to be from the graph where those look like they are. So I know I'm definitely going to be integrating from negative 1 to 2. And I know my pi is going to be out front. And now I want my outer radius squared minus my inner radius squared. So let's think about this. From the axis of rotation to the top, let me go a little darker here. From the axis of rotation to the top, that's my outer radius. So that's going to be x plus 2 squared minus my inner radius is from my axis of rotation to the bottom function, which will be x squared. And again, that would be dx because we're slicing perpendicular to the x-axis. So that would be my setup, and then I can integrate that. All right, last one is this one, and now look where we're rotating. We're rotating around the line x equals negative 1, so we're rotating around this right here. So notice what this will look like now. This is going to rotate out to here. This is going to rotate to here. We're going to have a curved edge over here. And then this inner function that is purple on my screen is going to kind of rotate like this. So again, it's going to look sort of like a bowl, right? Curved on the edges. The bottom is sliced off, and it'll have curved in edges on the side. So notice when we slice this, we're going perpendicular to the y-axis to get those washers. So I want this in terms of y. So I think this needs to be dy. So what I want to think about doing here is finding my outer radius, finding my inner radius, and then integrating that area in terms of y, with my y values as my bounds. So looking at this here, my lower bound on my y values is 0. My upper bound on my y values is 1. So I know already that my integral here is going to go from 0 to 1 because these need to be y values. I know the pi is going to be out front, so that's all good. Now what I need in here is my outer radius minus my inner radius squared, each individually, right? dy, because that's going to be with respect to y. So let's think about our outer and our inner radius. The line that we are revolving around here is this, x equals -1. So for my outer radius, I'm going to do this one in orange. We're going to go from our axis of rotation to the outermost function, right? But I want that in terms of y. So that is the function y equals x squared. In terms of y, this would be x equals square root of y. So that radius is the outer square root of y minus the inner, which is -1. So that radius is square root of y minus -1. And then I'm going to square that because that's my outer radius squared, right? R squared. Now my inner radius, let's take a look at that. Let's pick a different color. Let's do green. I'm going to go from my axis of rotation to the inner function. And that inner function is y equals square root x. So in terms of y, that is x equals y squared. And again, since this is -1, it's going to be y squared minus -1, and I'm going to square that whole quantity. And because we're subtracting our radii, we need to subtract that. So this is that same equation that we had before, right? Pi times the integral of your outer radius squared minus your inner radius squared, dx or dy. But you have to think about the fact that your radius here is going from this function to that function. So you need to do outer minus inner. So I know these can be a little bit tough. They're going to come with more practice, and we'll continue to practice them. But remember, at the end of the day, volume is just an accumulation of area, right? Volume is just an accumulation of area. So what we're really doing is we're finding the area function, and then we're accumulating that. And that's where that formula comes from. So check this summary, send me questions as always, and we'll continue to work on this more before your tests. So I'll see you guys soon. I hope you have a good day.